students, welcome to Vari Medical Academy. So, உங்களுக்கு எல்லாத்துக்கும் ஒரு குட் நியூஸ். Vari Medical Academy சார்பாக இனி வரும் நாட்கள் டெய்லியும் ஒவ்வொரு டாபிக் நம்மளுடைய faculty members லைவ் வீடியோ ஸ்ட்ரீம் உங்களுக்கு கொடுக்க போறாங்க. Wish you all the best my dear future doctors. டாபிக் ஏதாவது வந்து கிளாரிட்டி வேணும் அப்படிங்கிற எந்த கண்டென்ட் ஆனாலும் கமெண்ட்ல தெரியப்படுத்துங்க. அதுக்குண்டான சொல்யூஷன் Vari Medical Academy சார்பாக கொடுக்க ரெடியா இருக்கும். இந்த மாதிரி வீடியோக்கள் உங்களுக்கு பிடிச்சிருந்தா மறக்காம லைக் பண்ணுங்க, சப்ஸ்கிரைப் பண்ணிக்கோங்க.
Good morning. Today we are going to discuss about the kinetic theory of gases. In that particularly we finished the syllabus. Today we are going to start the specific heat of gas. Specific heat of gas. Look at this. In this we have monoatomic gas is there, diatomic gas is there, polyatomic gases is there. So what is the specific heat of monoatomic gas, diatomic gas and polyatomic gas? First we need to take first one, monoatomic gas. Monoatomic gas specific heat. Monoatomic gas specific heat. Specific heat. Yeah. In this, first we need to take the, what is the energy of kinetic energy of the gas molecule? We know that kinetic energy of the gas molecules of kBT. Energy of the gas molecule E is equal to of kBT. Of kBT. Here kB is the Boltzmann constant. Boltzmann constant. And T is the absolute temperature. Absolute temperature. E is equal to half kBT. This is according to equipartition of law. According to equipartition of gas laws, the energy is associated with the half kBT. Half kBT. For monoatomic gas molecules, we have 3 degrees of freedom. We know that. For monoatomic gas molecules, we have 3 degrees of freedom. Kinetic energy is associated with each degrees of freedom is half kBT. This is each degree of freedom. Each degree of freedom is half kBT. For monoatomic gas molecules, for monoatomic gas molecules, degrees of freedom are 3. For monoatomic gas molecules, degrees of freedom is 3. So according to equipartition of theory, the kinetic energy associated with half kBT. So 3 degrees of freedom. 3 degrees of freedom. For 3 degrees of freedom, the energy, average energy, take as average energy E bar is equal to 3 into degrees of freedom into E. Okay, degrees of freedom into E, that is E bar is equal to 3 into half kBT. 3 into half kBT. E bar is equal to 3 by 2 kBT. 3 by 2 kBT. Here mention it, just half kBT for each degrees of freedom. For 3 degrees of freedom, E bar is equal to 3 by 2 kBT. Nothing but average energy of each molecule, that is 3 by 2 kBT. Now internal energy per molecule. Internal energy for molecule, 1 mole of molecule, we need to take U is equal to E bar into Na. Take as Na is the Avogadro number. Na is the Avogadro number. So we can write as U, internal energy U is equal to 3 by 2 kBT into Na. Internal energy for one molecule of gas molecule, 1 mole of gas molecule, U is equal to 3 by 2 kBT. This is U is equal to 3 by 2 kb into Na is nothing but R, because kb is equal to we know Na by R. kb is equal to R by Na, not Na by R by Na. Okay, so if you substitute the kb value, then you are getting U is equal to 3 by 2 RT. This is the internal energy. Internal energy of gas molecule. Internal energy of gas molecule U is equal to 3 by 2 RT. Now, specific heat of a monoatomic gas at a constant volume. Specific heat of monoatomic gas at a constant volume is constant volume is we can take as CV is equal to du by dt. CV is equal to du by dt. Yeah, just substitute the u value in this equation. CV is equal to du by dt of 3 by 2 RT. Just, yeah, see this. CV is equal to du by dt. Then CV is equal to d by dt of 3 by 2 RT. 3 by 2 R is the constant. Then it will become CV is equal to 3 by 2 R into dt by dt. So we can write as 3 by 2 R. Specific heat of monoatomic gas at constant volume is 3 by 2 R. Next, specific heat of gas at constant pressure is the Cp. Cp minus Cv is equal to R. We know specific heat of monoatomic gas at constant pressure is specific heat of gas, specific heat of monoatomic gas at constant pressure, at constant pressure is Cp is equal to Cv plus R. This is from Cp minus Cv is equal to R. Just substitute the Cv value. This is 3 by 2 R. So Cp is equal to 3 by 2 R plus R is equal to 5 by 2 R. This is 5 by 2 R. So Cp is equal to 5 by 2 R and Cv is equal to 3 by 2 R. From this, we need to find the specific heat ratio also. Cp by Cv, that Cp by Cv is nothing but gamma value or specific heat ratio value. Yeah, that is, here it is, specific heat ratio, specific heat ratio of monoatomic gas, is, specific heat ratio of monoatomic gas is Cp by Cv. Cp by Cv is equal to 3 by 2 R. 3 by 2 R by 5 by 2 R. 5 by 2 R. Cp by Cv is nothing but gamma. Gamma is equal to, it will become Cp by Cv, reverse. Here it is, 5 by 2 R. 5 by 2 R by 3 by 2 R. RR gets cancelled, then 2 also gets cancelled, then it will become 5 by 3. So gamma is equal to 1.666, it will come 666. So 1.67, gamma is equal to 1.67 is the specific heat ratio of monoatomic gas. Specific heat ratio of monoatomic gas. Yeah, look at that. For monoatomic gas molecules, internal energy is and kinetic energy is with degrees of freedom and internal energy CV, CP, 5 points. First is the kinetic energy, E is equal to half kBT. Average kinetic energy with 3 degrees of freedom, E bar is equal to 3 by 2 kBT. Third point, internal energy for 1 mole of gas molecule. Internal energy for 1 mole of gas molecule is U is equal to 3 by 2 kBT into Na. This is nothing but U is equal to 3 by 2 RT. 3 by 2 RT. From this, CV is equal to, we are getting CV is equal to 3R by 2. 3R by 2. And Cp is equal to, we are getting 5 by 2 R. 3 by 2 or 5 by 2 R. And the ratio we are getting 1.67. These 5 points we discussed in this. Energy of the kinetic energy of the gas molecule, monoatomic gas molecule associated with the degrees of freedom. That is, for monoatomic gas molecules have the 3 degrees of freedom. So we are getting 3 into kinetic energy, that is E bar, take as average kinetic energy, that is 3 by 2 kBT. From this, internal energy also we need to write. For internal energy of 1 mole of gas molecule is 3 by 2 kBT into Na. From that, 3 by 2 RT. So Cv is equal to 3 by 2 R, Cp is equal to 5 by 2 R, and gamma is equal to 1.67. This is the monoatomic gas specific heats. Yes. Next, specific heat of diatomic gas. Diatomic gas like nitrogen, oxygen, etc. This type of molecules have the different degrees of freedom. First, monoatomic gas molecules. Monoatomic gas molecules, helium, neon, argon. This type of gas molecules have the 3 degrees of freedom. Based on 3 degrees of freedom, we did that monoatomic gas molecules, kinetic energy, average energy, CV value, CP value, right? Similarly, specific heat of diatomic gas molecules. For diatomic gas molecules like oxygen, nitrogen, etc. We need to take this type of gas molecules. Energy is common. Half kBT. E is equal to half kBT, where kB is the Boltzmann constant and T is the absolute temperature. But this gas molecules energy is associated with the degrees of freedom. For diatomic gas molecules, 5 degrees of freedom are there. 3 translational degrees of freedom and 2 rotational degrees of freedom. For monoatomic gas molecules, only 3 degrees of freedom. 3 translational degrees of freedom is there. For monoatomic gas, only 3 degrees of freedom, which is related to translational degrees of freedom. But diatomic gas molecules have 5 degrees of freedom. In that, 3 are the translational degrees of freedom and 2 are the rotational degrees of freedom. So average energy of the diatomic gas molecule is degrees of freedom into half kBt. Average kinetic energy of the diatomic gas molecules which is associated with the degrees of freedom of the gas molecule. Okay, then that is E bar is equal to average energy is equal to 5. This is 5 degrees of freedom is 5 into 1 by 2 kBt. This is E bar is equal to 5 by 2 kBt. 5 by 2 kBt, where kB is the Boltzmann constant and T is the absolute temperature. Next we want the internal energy for 1 mole of gas molecule. Internal energy for 1 mole of gas molecule. Internal energy per 1 mole of gas molecule. Internal energy for 1 mole of gas, diatomic gas, 1 mole of diatomic gas is, this is U is equal to E bar into Na, Avogadro number. 1 mole of gas molecules, how many molecules are? So that is Avogadro number equal to Avogadro number U is equal to E bar into Na. This is, we can write as U is equal to 5 by 2 kBt into Na. 5 by 2 kBt into Na. This is, so we can write as this is U is equal to 5 by 2. In the place of kB we can write as R by Na. Boltzmann constant is equal to R by Na, universal gravitational constant divided with Avogadro number is nothing but the Boltzmann constant into T into Na. Na gets cancelled, then we get 5 by 2 R. This is the internal energy of the diatomic gas molecule. This is internal energy of the diatomic gas molecule. From this, we want the specific heat of diatomic gas molecule at constant volume. Specific heat of diatomic gas molecule at constant volume. Next point, specific heat of diatomic gas molecules at constant volume. Constant volume is Cv is equal to du by dt. Cv is equal to du by dt, internal energy by absolute temperature. So this is, we can write as Cv is equal to, this is 5 by 2 RT, right? This is equal to d by dt of 5 by 2 RT. d by dt by dt is nothing but 1. So we get Cv is equal to 5 by 2 R. Cv is equal to 5 by 2 R. This is the specific heat of a diatomic gas at constant volume. Specific heat of a diatomic gas at constant volume is Cv is equal to 5 by 2 R. Look at that. At specific heat of diatomic gas molecules is nothing but oxygen, nitrogen, like this type of molecules, energy is of kBt and average energy is 5 by 2 kBt. Internal energy is 5 by 2 RT for 1 mole of gas molecules and CV is equal to 5 by 2 R. Next we want the CP of specific heat of diatomic gas at constant pressure. Nothing but, if you want we can write here, specific heat of diatomic gas molecules at constant pressure is CP is equal to CV plus R. We have CP minus CV is equal to R. From that, CP is equal to CV plus R. So CP is equal to, this is 5 by 2 R plus R. This is equal to 7 by 2 R. CP is equal to 7 by 2 R. This is the specific heat of diatomic gas at constant pressure. Last point we want that ratio of specific heats at constant pressure and constant volume is CP by CV is. CP by CV value we can get from these two equations, CV value from CP value, which is CP by CV, the ratio of CP by CV is, the ratio of specific heats is at constant pressure and at constant volume is CP by CV is equal to 7 by 2 R by 5 by 2 R. 2 cancel, RR gets cancelled, then CP by CV is called as the gamma. CP by CV represents with gamma. So gamma is equal to 7 by 5. 5 ones are, 5 ones are, 5 fours are. So gamma is equal to 1.4. Gamma is equal to 1.4. The specific heat ratio for diatomic gas molecules is 1.4. For monoatomic gas molecules, it is 1.67. For diatomic gas molecules, it is 1.4. Yeah, here it is, one point is there. At room temperature for monoatomic gas molecules, 1.67. Gamma is equal to 1.67 for monoatomic gas molecules. At room temperature for diatomic gas molecules, gamma is equal to 1.4. Gamma is equal to 1.4. If the temperature increases, the value of the gamma will be changed, because if the temperature increases, the molecules getting the vibrational motion also, then degrees of freedom will be changed. At higher temperature, the degrees of freedom will goes to 7. Degrees of freedom goes to 7. Then kinetic energy, internal energy, CP by CV values will be changed. That's why gamma value also change at higher temperature. We will discuss it in the next video. Thank you.